Welcome back to Quantitative Reasoning. In the previous tutorial, we learned how to build a linear model, extract its coefficients, and plot the regression line on a scatter plot. In this tutorial, we learn how to obtain further numeric information about the model. We'll also learn how to make a residual plot. Last time, we fitted a linear model for upper arm length as a function of body height. You can click on the link below this video to access the data again. Here are the commands we used last time. I mentioned in our previous tutorial that the function lm returns a data structure of class lm, which is more complicated than a vector or a data frame. When we type the variable name model in the console and press the return key, R only reveals the y-intercept and the slope, which are only the tip of the iceberg. R prints out more information when we run summary in parentheses model. During this course, we can only scratch the surface of the statistical information contained in R's output. An easily interpretable piece of information is multiple R squared, which our textbook simply refers to as R squared in chapter 7.6. It can be interpreted as the fraction of the data's variance that is accounted for by the linear model. If we want to see only the R squared value and omit the remaining output from the summary function, we use the command summary in parentheses model $r.squared. We conclude that 53.3% of the data's variance is explained by the linear model. The remaining 46.7% are due to the scatter of the residuals. As our textbook explains in chapter 7.1, the residual of an observation is the observed value minus the predicted value. This plot shows the residual of the data point highlighted in blue. We can obtain the residuals for all observations with the function residuals. The residuals play a key role in assessing whether a linear model is a good description of our data. Our textbook suggests that we should always make a scatter plot of the residuals after fitting a linear model. In figure 7.5 on page 209, our textbook uses the observed value as x-coordinates, whereas the unnumbered figure on page 215 has the predicted values on the x-axis. The only difference between using the observed or predicted values is a linear scaling of the x-axis, which doesn't affect the conclusions we draw from the plot. Using the predicted values as x-coordinates is generally more common in the literature. It's also easier to produce such a plot with R, especially if the data contain missing values, as it's the case in our example. We can simply use the plot function with the linear model as first argument and which equals 1 as second argument. Don't worry too much about the meaning behind which equals 1. There are various diagnostic plots that the plot function can produce for a linear model. With the arguments which equals 2, which equals 3, etc., we get other types of diagnostic plots. In this course, we only need the residual plot, so we'll generally work with the argument which equals 1. As usual, we can add a main title to the plot with the argument main. We can also change the cryptic formula on the second line of the x-axis label with a sub.caption argument. If the linear model is appropriate for a dataset, then the point pattern in the residual plot shouldn't have any noticeable curvature. As a visual aid to judge whether the data are curved, R inserted a red lowest curve into the plot. In our example, the lowest curve is nearly straight, which indicates that the data satisfy the straight enough condition of our textbook. Another condition for applying a linear model is that there are no outliers that would affect the linear trend. R writes the indices of the 3 most extreme outliers next to the corresponding points in the plot. For example, the upper arm length of the participant in row 198 of BM has a large positive residual. It's always a good idea to check whether there's something interesting or suspicious about outliers. In this example, data point 198 doesn't have much influence on the line that we fit to the data, so there's no compelling reason to take any special action regarding this data point. Another condition on the residual plot is that the plot doesn't thicken. That is, the spread in the y direction shouldn't depend strongly on the x value. The cloud of points should be equally thick on the left and on the right. If this condition is violated, we may need to re-express the data before fitting a linear model. Our example satisfies all conditions for linear regression. Consequently, it's appropriate to use a linear model for upper arm length as a function of body height. Suppose that we encounter a group of 20 to 25-year-old women who aren't in our dataset. If we know their body heights, what would be our predictions for their upper arm lengths? In our next tutorial, we learn how to predict the y-coordinate for a given x-coordinate with the function predict. Let's recap the main points of this tutorial. If a linear model is stored in the variable model, then summary in parentheses model returns various statistical pieces of information. We obtain the r² value with summary in parentheses model $r.squared. We get the vector of the residuals with residuals in parentheses model. We make a residual plot with plot in parentheses model, comma, which equals 1. A residual plot should satisfy the 3 conditions stated in chapter 7.7 of our textbook: the straight enough condition, the outlier condition, and the does the plot thicken condition. If any of the conditions is violated, a linear model isn't ideally suited for our data. We may need to re-express the data, check the reasons behind outliers, or use a different statistical model. Next time, we learn how we can make predictions on the basis of a linear model. See you soon.